Hey, before we continue, please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.
Hello, welcome to the Algebra course. My name is Mike and I will be teaching you this course. So what is algebra? Well, loosely translated from its Arabic roots, algebra means balancing and restoring. But that's a little bit boring, and to us, what does that mean so far? Well, it means nothing really. I prefer to think of algebra, like all math, as the mystery of the unknown. And what do I mean by that? Well, before you get to algebra, you do things like adding numbers, subtracting numbers, multiplying, dividing numbers, and there's really no mystery there. You're just kind of doing arithmetic. You're combining numbers together. In algebra, we have new things called variables or unknowns that we represent with letters. So for example, we have something like x plus 1 equals 5. We can think of x as just standing in the place for a number. What number needs to go there? So there's some mystery here. We're on the hunt for the number that goes in place of x. Well, this example is not too hard. If instead of x, if we had in place of x there in that equation, if we had 4, then 4 plus 1 equals 5. That's certainly true. So instead of that x, we need to put a 4. So what we say is that x must be equal to 4. And there we go. We've solved our first algebraic equation. We started with an unknown called a variable x, and we found out it had to be 4. So the key idea here is that x is what's called a variable or an unknown. They're synonymous. And what do we need to know about variables? Well, variables just stand in the place of a number. In our example, the letter x, the variable, stood in place of 4. Also, variables are usually written as letters of the alphabet. In this particular example, we chose the letter x. But it doesn't have to be x. And in fact, let's see another example of an equation with a variable. So how about a plus 10 equals 12? So what has to go in for a? What does a stand in the place of? Well, it's not too hard to see that if we put a 2 where a is, then we get a true equation. So a is equal to 2. A is standing in the place of the number 2. And if you really want to see that, we can write this out. 2 plus 10 certainly equals 12. So we can see that a really was just standing in the place of 2. And that's the beginning of algebra. Instead of working with just numbers, we start working with variables, and that's a very powerful tool. Okay, we'll see how powerful it is, and we'll see lots more examples and really dive into this when we get into the course. See you then. In this video, we're going to talk about different types of numbers. If you have to memorize the different types of numbers for a class, then this is a great place to start. If not, then we're going to get on the same page by just quickly reviewing these different types of numbers. So we start with the natural numbers, which are sometimes called the counting numbers because we start at 1 and we just count up from there. 1, 2, 3, 4, 5, 6, so on and so on until we get to 100, a million, a trillion, and it just keeps going. If we want to add in 0, we can do that, and sometimes we write that little subscript of a 0. Sometimes we call these the whole numbers, the natural numbers with 0. That's not too important. Now, the integers have all the natural numbers, they have 0, and they have these negative numbers. So an example of an integer is something like -7. Now, -7 is an integer, but it's not a natural number because there's no negatives in the natural numbers. On the other hand, something like 20 is both a natural number and an integer. We can clearly count up to 20 in the natural numbers, and if you look at the integers include all the natural numbers, 1, 2, 3, 4, 5, and so on. Now, what's an example of a number that's not an integer? Well, how about something like a fraction? Now, when we move to if we want to include all the fractions, then we move to the rational numbers. So, for instance, 1/2 is a rational number, but it's not an integer. Now, 1/2 is a rational number because if you look, 1 is an integer in the top and 2 is an integer in the bottom. So when we make a fraction with integers, that's a rational number. Now, can you think of any examples of a number that is both a rational number and an integer? Well, 5 is both. Why? Think about it. 5 is definitely an integer and a natural number for that matter, but it's also a fraction because 5 is the same thing as 5 over 1. Now 5 is an integer and 1 is an integer, so we can write 5 as a fraction of integers. So 5 is a rational number and an integer. In fact, all the integers are rational numbers. Now, what about things that are not rational numbers? Well, the square root of 2 is not a rational number, but it is something called a real number. So real numbers are all the rational numbers, all the fractions, and there are these mysterious things like the square root of 2 and the square root of 3, and numbers that we call irrational. So, for example, 5/2 is a fraction, so it's both a real number and a rational number. But the square root of 2 is only a real number. We'll talk more about the real numbers at the end of the video, but they're really, really, really important. They're the numbers we'll be using most often in this course. Finally, we get to the complex numbers, which are just real numbers with imaginary numbers, things of the form a plus bi, where a and b are real and I is the imaginary number square root of -1. Now, if the complex numbers right now seem mysterious and weird to you, don't worry about it. We'll talk about it later. But let's revisit the real number line, or the real numbers. So this is the real number line, and it's just a continuous line of numbers. You can see we have all the integers, 1, 2, 3, and so on. We also have everything in between. So, for example, right where that green dot is, that's perhaps the square root of 2, because the square root of 2 is approximately 1.414, and it keeps going on forever. So it's just a little less than 1.5. Now, the interesting thing about this is that if we were to draw a number line with only rational numbers, so only fractions, well, we already talked about the fact that the square root of 2 is not a rational number. It's not a fraction. So if we drew a number line with only fractions, there would be holes in it. There would be a hole where the square root of 2 goes. So the real number line is really special. It has this property that every number is there. There's no holes or jumps or gaps. And we'll use the real number line in that sense, that basically when we can think of it as all the numbers on that line, the whole line is continuous and filled with numbers. Okay, see you in the next video. In the last video, we learned how addition and multiplication have this nice property called the commutative property. Now we're going to learn a new property that addition and multiplication both have, and it's the associative property. So addition is associative. Let's start with addition here. So A plus B as a group plus C is the same thing as A plus the group B plus C. So really it tells us something about how we're grouping addition, where we write these parentheses. And really it's saying it doesn't matter where we write them because they're the same. So let's see an example. 9 plus 3 plus 5. And we'll do 9 plus 3 as a group. Well, this is equal to 9 plus the group 5 plus 3, or 3 plus 5. So 9 plus 3 is 12 plus 5. And then on the other side, we're going to get 9 plus 8. 12 plus 5 is 17. 9 plus 8 is 17. And so we can see the associative property in action. Doesn't matter where we put the parentheses, both sides are equal. Since it doesn't matter where we put the parentheses, what we're going to do is just drop them. The parentheses don't tell us anything interesting, so we don't need them. It doesn't matter where we put them, so why put them anywhere? Okay, so that was addition. Multiplication is the same. Multiplication is associative. So we write that as A times B as a group times C is equal to A times the group B times C. So it's the same thing, and let's see an example of this. Five times 3 as a group is equal to 5 times the group 3 times 2. So 5 times 3 is 15 times 2. And then on the other side we'll get 5 times 6. And 15 times 2 is 30. 5 times 6 is 30. So you can see that both sides are equal. If you're wondering if anything isn't associative, in the next video we'll see that subtraction is not associative. And we'll see how that works. Okay, see you then. We have two groups of marbles on screen. 5 blue marbles and 2 red marbles. And if I asked you to tell me how many total marbles are there, some of you might write, well, there's 5 blue ones plus 2 red ones, so there's 7 marbles in total. But some of you might start counting with the red, and you'd say there's 2 red ones plus 5 blue ones, which still gives you a total of 7 marbles. So the important thing here is that 5 plus 2 is equal to 2 plus 5. It doesn't matter which order we add in, because we're counting the same number of marbles. And this is a really important property of addition. It's called the commutative property of addition. And it says that if we have any two numbers, a and b, then a plus b is equal to b plus a. So it doesn't matter which order we add two numbers in. And we have something similar for multiplication. So let me write some dots on screen here. And I want you to count how many dots there are on screen. Or tell me how many. You don't have to count them, but tell me how many dots there are. Some of you might say, well, there's 5 groups of 3. Here's a group of 3, and there's 5 of them. So that's 5 groups of 3, or in other words, 5 times 3. And so there's 15 dots on screen. Others of you might look at it a little bit differently. Instead of seeing 5 groups of 3, maybe you see 3 groups of 5. So here's a group of 5, and there's 3 of those, so that's 3 times 5, which still gives us 15 total dots on screen. So again, the important thing here is that 5 times 3 is equal to 3 times 5. And there's nothing special about 5 and 3. This works for any two numbers. So this is the commutative property of multiplication. and we write A times B is equal to B times A. So given any two numbers, you can multiply them in either order you like. These two properties seem simple, the commutative property of addition and the commutative property of multiplication, and they are simple, but they're really important, so they'll be good to know. Okay, see you in the next video. I want to talk to you about simplifying fractions, or what's sometimes called canceling fractions. So let's start with the basics. 5 divided by 5 is what? It's 1, right? Any number divided by itself is just 1. So negative 1,131 divided by itself, again, is just 1. What about fractions? Something like 3/7 divided by 3/7. Well, a fraction is just a number, and so we're dividing it by itself, so we get 1. What about 0? 0 divided by 0. Well, this is not equal to 1. This is the only exception, and it's because we can't divide by 0. If we tried to divide by 0, the universe would split open and your mother would cry. It just would be terrible. So 0 divided by 0 is undefined, and that's the only exception. So we end up with this nice little rule. If a is not equal to 0, then a divided by itself is equal to 1. So what does this have to do with canceling fractions? Well, let's see a really simple example. 2 divided by 4 is the same thing as 2 times 1 divided by 2 times 2. Well, because we know the way fractions multiply, that's the same as 2 over 2 times 1 over 2. But 2 over 2, we just talked about, that's just 1. So we're left with 1 times 1 over 2, or in other words, 1/2. And 1 times anything is just that thing, so we're just left with 1/2. So it took us quite a few steps, but we simplified 2/4 to 1/2. Let's see another example. 6 over 27. Well, 6 is 3 times 2, and 27 is 3 times 9. And again, we can split this up into two fractions. So we end up with 3 divided by 3 times 2 divided by 9. The 3 over 3, that just becomes a 1. So we're left with 1 times 2 over 9, which of course is just a 2 over 9. So this is taking a lot of writing. It takes quite a few steps. So maybe we want to abbreviate this. We know how everything's going to work out. We're going to end up multiplying by 1. So instead of writing out those steps, we're going to do something like this. Let's see this again, only with an abbreviation. So 6 over 27 is 3 times 2 over 3 times 9. And we know that 3 is going to cancel to 1, so we'll just cross it out. And that's an abbreviation for those steps underlined in orange. And we end up with 2/9. Okay, so this can actually be really useful. Let's combine simplifying fractions, what we're doing in this video, with some things we've already learned. What if we had something like 3 times 3 over 47 times 2 over 13, 13 times 3 over 47 times 2 over 13 times 47. Well, it looks like the 13 in the denominator there and the 13 on the left maybe will cancel, and the 47 in the denominator and the 47 on the right might cancel. So since multiplication is commutative, something we've already learned, we can rearrange this any way we want. So we'll rearrange it this way. Let's put the 13s together and the 47s together. Also, multiplication is associative, which means we can group it any way we want. So let's not only put them next to each other, but let's actually group them. And now we know the way fractions multiply. That's something we've already learned. 3 times 2 over 13 is just 13 times 2 over 13 is just 13 times 2 over 13. We get something similar over on the right-hand side. And now we can just cancel. But since this is our first example, let's just go through one more step. So 13 times 2 over 13 times 1, right? 13 is the same as 13 times 1. So we'll just put that 1 in there. And 3 times 47 is the same as 47 times 3. And 47 is the same as 47 times 1. And now we're all set to cancel. So we're just left with 2 over 1 times 3 over 1. Well, 2 over 1 is just 2, and 3 over 1 is just 3. So this is 2 times 3, which is equal to 6. And it took us quite a few steps because I wanted to write everything out so we could see how this works. But the main point here is that we can use all of our rules to simplify that multiplication. Okay, what if we have addition instead of multiplication? Can we cancel then? Something like this. Well, the answer is definitely no. Doing something like that is wrong. You don't want to do that. Why not? Well, let's see. If we canceled, we'd be left with 1/3. So instead of canceling, let's see what happens if we just do this addition and try and simplify. So 5 plus 1 is 6, 5 plus 3 is 8, and then we're left with 6 is 2 times 3, 8 is 2 times 4, and now we know those 2's cancel, and we're just left with 3/4. Well, 3/4 certainly is not the same thing as 1/3. If we had canceled the 5's originally, we would have gotten 1/3, but of course 3/4 does not equal 1/3. So that's just an example of why this doesn't work out. It doesn't work out because we need to be multiplying by something over itself. Because when we're multiplying by something over itself, we're really just multiplying by 1. And that's where the simplification comes from. But when we have addition, we don't have any multiplication, so we're certainly not multiplying by 1. Okay, see you in the next video. I want to talk to you about division, but before we do that, we should do some review of fractions. So if we want to multiply two fractions, a over b times c over d, we just multiply across the top, so a times c, and then multiply across the bottom, so b times d. Really simple. Multiplying fractions is really easy. So let's see an example. 3 over 5 times 2 over 7. Well, we just get 3 times 2 in the numerator over 5 times 7 in the denominator. So it's just 6 over 35. Really, really basic stuff. Let's do another example. How about negative 5 over 8 times 9 over 11? Well, this is just negative 5 times 9 over 8 times 11. And negative 5 times 9 is negative 45, and 8 times 11 is 88. Just to be thorough, why don't we do one more example and then we'll talk about something different. How about 1/3 times 40 over 41? Well, 1 times 40 is just 40 over 3 times 41. So this is 40 over 123. Okay, so we figured out how to multiply fractions. It's really, really simple. But you might have a question lingering. And that question is, how do I multiply a number by a fraction? We know how to multiply fractions by fractions, but let's see an example of multiplying just a number by a fraction, an integer. So for example, 7 times 2/3. Well, the key to doing this is just to remember that 7 is equal to 7 over 1. So we can turn 7 into a fraction. And now we have 7 over 1 times 2 over 3, which of course is 7 times 2 over 3 times 1. which is just 3. So we have 14 thirds, 14 over 3. Now this comes up so often we can single it out as its own special case. So we can write our own rule for a number times a fraction. A times c over d is equal to a times c over d. And now if we just use this rule here that we derived, we'll have 7 times 2 thirds is just equal to 7 times 2 over 3, which of course is 14 thirds. So all we did was we skipped the step where we wrote 7 as 7 over 1. We don't need to really write that every time, as long as we understand how all this works. Okay, I hope that was a good review. See you in the next video. I want to talk to you about subtraction. Subtraction is kind of nasty. It doesn't have very many good properties that we like. For instance, 6 minus 2 is not equal to 2 minus 6. Why? Because 6 minus 2 is 4, and 2 minus 6 is negative 4. So obviously 4 is not equal to negative 4. So subtraction is not commutative. And the example we just gave is 6 minus 2 is not equal to 2 minus 6. There's other things wrong with subtraction. For instance, subtraction is not associative. So an example of that would be 9 minus 4 grouped minus 1 is not equal to 9 minus parentheses 4 minus 1. And we can go through this just to prove it to ourselves. 9 minus 4 is 5 minus 1. And then on the other side we have 9. Well, 4 minus 1 is 3, so 9 minus 3. Those are not equal because 5 minus 1 is 4, and 9 minus 3 is 6. So subtraction is not associative. And there's another reason subtraction is not that great. But first, let's just write our example down. So our example here was 9 minus 4, parentheses, minus 1, or parentheses 9 minus 4, and parentheses minus 1, is not equal to 9 minus parentheses 4 minus 1. Okay, another reason that subtraction is not that great is because sometimes it can be confusing with the order of operations. So for instance, 10 minus 6 plus 2. Maybe we're not sure, should we do subtraction first or should we do the addition first? So we think of the order of operations, parentheses, exponents, multiplication, division, addition, and subtraction. And that looks like we're supposed to do addition first. Addition comes before subtraction. So this would be 10 minus 8, which would be 2. But that's wrong. That is the wrong answer. What we forgot is that what the order of operations really says is then when you have only subtraction and addition left, do everything from left to right. So this is really 10 minus 6, which is 4, plus 2, which is equal to 6. And that's the right answer. So the third reason subtraction isn't that great is because subtraction can be confusing with the order of operations if we're not careful. And our example for this one is 10 minus 6 plus 2. But all is not lost. There's something we can do. We can actually turn subtraction into addition, because a minus b is an abbreviation for a plus negative b. So let's look at our first example. How would that work? Well, 6 minus 2 is equal to 6 plus negative 2. And now since we're doing addition, we know this is commutative. So we can change the order. So now we have negative 2 plus 6. Notice in this example, the negative sign stays with the 2. In our original example, the negative sign went to the 6. That was the problem. The negative sign was on the wrong number. Okay, so when we think of subtraction as addition of a negative number, we get commutativity back. A little note about the notation here. Why do we put parentheses around the negative sign? It's really because doing it that way is ugly and unclear, and you might even confuse somebody if you're not very neat. So instead, what we do is we put parentheses around the negative sign so that everything is really clear. If we look at this, it's very clear what we mean. We mean 6 plus negative 2. And now anybody looking at that will know exactly what you mean. Okay, so that's just a note about why we put parentheses around the negative sign. Let's talk about what happens with associativity when we think of subtraction as addition of a negative number. Well, subtraction really does become associative again because we're turning it into addition. So let's just look at our example here. 9 minus 4, parentheses 9 minus 4 end parentheses, minus 1, is equal to 9 plus negative 4 plus negative 1. And now, this is all addition, and since addition is associative, it doesn't matter where we put the parentheses. We could put them around the 9 plus the negative 4, or we could put them around the negative 4 plus the negative 1. And why don't you try doing that at home? See if you get the same answer. You should, because addition is associative. Okay, and finally, let's look at our third example. Does this fix the problem? So 10 minus 6 plus 2, if we think of this as 10 plus negative 6 plus 2, now if we do the negative 6 plus the 2 first, we would get negative 4 from that. So 10 plus negative 4, which is equal to 6. So even though we did the negative 6 plus the 2 first, we got the right answer. Okay, so the important thing to take away from this video is that subtraction is not commutative and it's not associative, but we can think of subtraction as addition of a negative number, and then we get all those nice properties back. Okay, see you in the next video. Let's look at factoring a cubic polynomial. So the way we're going to do this is we're going to factor by grouping. And for now, that's the only way we're going to look at. Later on in the course, we'll talk about factoring with the rational roots test and synthetic division and things like that. But for now, we're just going to group it. So how does that work? Well, we group the first two terms together, and then we add the second two terms, the group of the second two. So this will be x cubed plus 6x squared plus, and then minus 4x minus 24. So we haven't changed anything. We just decided to group these into pairs. And now we factor out of each group what we can. So on the left side, we can get an x squared out of each term. And that just becomes x squared times x plus 6. And then we have to add to that, well, what can we get out of the next term? Well, we can get an entire negative 4, right? This will be negative 4 times x x plus 6, right? Because negative 4 times positive 6 becomes that negative 24. And now we have an x plus 6 multiplying both terms. So we can just factor that out. So this becomes x squared minus 4 times by x plus 6. And we're almost done, but remember the difference of squares said if we have x squared minus a squared, this is always going to be equal to x minus a times x minus b, or sorry, plus x plus a. Sorry, there's no b involved. X minus a times x plus a. Well, that's what we have here. Isn't this x squared minus 4 is the same as x squared minus 2 squared times by x plus 6. So now we can use the difference of squares to factor this completely into x minus 2
times x plus 2 times by, oops, sorry, I missed a parenthesis up there, times x plus 6. And now we're done. This is as simple as we can get this problem. So we factored by grouping. That's how we're going to do it. What happens if you have a coefficient in front of the x term? So let's look at that. What if we had something that looked like 3x cubed plus 9x squared plus x plus 3. What are we going to do now? Well, we're going to do the exact same thing. Nothing changes. So when you have a cubic polynomial, if it factors by grouping, if this grouping method works, it's really, really quite simple. So we're just going to set up our groups here. And we have 3x cubed plus 9x squared plus x plus 3. Well, what can we factor out of the group on the left? We can take out an entire 3x squared, right? And now we'll just be left with, on the inside, we'll be left with just an x plus 3, right? And now plus, well, what's common to x and 3? The only thing common to both of those actually is just the number 1. Right? 1 times x is still x, and 1 times 3 is still 3. So we're going to factor out of 1. It's really not factoring it out. It's always been there, but we're going to write it just to make this more clear. And now we have an x plus 3 common to both terms. So we factor that out. So this becomes 3x squared plus 1 times by x plus 3. And that's as simple as we can get this particular problem. But as you can see, factoring by grouping it makes these problems really easy. So until we talk about the rational roots test, this is the only way we're going to try and factor cubic polynomials. Okay, see you in the next video.
Please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.